Here's an example of a test problem. Let's say we've got this compound here. The first thing you want to do is figure out whether or not it's activating or deactivating. And the way we can do that, let's go ahead and draw it. Alright, so now we've got an oxygen here that's single bonded, and it's going to have a delta minus on it. And that's because it's got these lone pairs of electrons that can be donated to the aromatic ring. Alright, so that's the first thing we need to do, is figure out what's going to go on with this oxygen. So we do that, and now we're going to, I'll put a delta minus on this O here, and I will go ahead and fill in my template. Since the BR is being added to the ortho position, the positive charge will end up here, and that's because the electrons from this double bond are forming a new bond with this C and the BR, and that leaves this carbon short of an electron, so that's going to be positively charged. Alright, so now we've got our two double bonds still being here. I'm actually going to draw these arrows on the outside of the ring, but there's nothing to stop you drawing them on the inside, going this way. That would be okay, just that I don't have enough room to do that here. And what that's going to do is push this double bond up to here and move the positive charge down to here. That double bond will still be there. Now what's happening here is that we've got two electrons in this bond, and they're forming a new double bond between this carbon and this carbon atom here. Now that's going to leave this carbon short an electron, so that's why the positive charge ends up moving down to this C. And we'll move the other double bond in the same way. And that leaves the positive charge over here. And now we can lose the H plus, and we'll end up getting that product. Alright, so we'll look at these resonance structures, and what we can see is that this will be a favorable resonance structure. Alright, it's a favorable resonance structure. And the reason it's favorable is because you've got a delta minus right next to a C plus. So that it has a stabilizing effect, which makes this a favorable resonance structure. Alright, we're going to do the same thing down here. We're adding the BR to the para position. That puts the BR on this carbon here, which means the positive charge will end up on the other side of where the double bond was. So we've got a plus here. And now we can go ahead and do our resonance structures. I'll do this one inside the ring. And that will give me a double bond here. And that puts the positive charge up here. This double bond will still be here. And now I can go ahead and move this double bond. Again, the tail of the arrow always starts on the bond and goes to the space in between these two carbon atoms. That's how we get the double bond there, and we'll have that one there. Alright, now we can also see that since we got the delta minus on the oxygen, again this will be another favorable resonance structure. So I'll just do the same thing there. So we've got two favorable resonance structures here. Lose the H plus, we can get our product. Alright, so because we got two favorable resonance structures here, we know we can get these two products, and these will be the two products that we'll put up here. Right, so we know that those will be the two products we get because of those favorable resonance structures that we're getting here. Now if we try this with the ortho, the positive charge will end up here. That's the first one. So we'll have a double bonds here and here. That's because we use this double bond in order to get the meta product. Right, so now we can move that double bond around. Again, the tail of the arrow is starting. The tail of the arrow is starting at the double bond and moving to the space in between these two C's. That puts a double bond here, positive charge here, and double bond is still there. Alright, so now we can go ahead and move this double bond. Now we'll put the positive charge down here, double bond here, double bond here. Now this doesn't have any favorable resonance structures. There's no instance where the positive charge is ending up directly underneath the delta minus of the oxygen, just because of where the positive charge can end up if it goes in the meta position. Therefore the meta product is not possible. So what I would write under here is no favorable resonance structures. And that tells the entire story then. No favorable resonance structures. So that explains why we get the ortho and para and why we do not get the meta. And that's a complete answer.